In the last class, we saw the simplest 2D NMR experiment which is 2D COSY, which is an abbreviation for correlation spectroscopy. In there we saw that you can only get the cross peaks or the chemical shift correlation between two protons which are directly J coupled to each other. But if they are not J coupled to each other, then you do not see any interaction or any peak between those two atoms, two hydrogens in a 2D COSY spectrum. So, this is useful sometime, whereas sometimes it may not be useful. Ideally you would like to know what a given proton is coupled to which all other protons in the molecule, that is directly coupled, but you would also want to know what are the other protons it is indirectly coupled to all the other protons in the molecule. So, that experiment information comes from another experiment known as total correlation spectroscopy 2D TOCSY, which is what we will see now. So, if you look at this picture here, so this is a pulse sequence for the 2D TOCSY experiment. So, what happens here is that you start first from a pulse 90-degree pulse, similar to what we see in COSY. You apply 90-degree RF pulse on a spin and all the spins in the molecule. This is a non-selective in nature. So, this will be applicable to all the hydrogen atoms. Now, once the hydrogen atom or once the proton is brought to the xy plane, this starts evolving in chemical shift. This is what we saw in the last class. So, this evolution is because of the chemical shift. Now, this decays in time because of the T2 relaxation. So, this is also something which we have seen. So, while this process goes on, we saw that in the case of COSY, it gets coupled to other hydrogen atoms in the molecule because of J coupling. In this case of 2D TOCSY, what we do is we allow for a short time here. So, the coupling to other hydrogen atoms during this portion is not of so much importance, but what we do is after some time we apply this box, what is shown here, that is known as isotropic mixing. Now, what is isotropic mixing? Isotropic mixing is nothing but weak RF irradiation applied continuously for 60 to about 80 milliseconds. So, this is basically just a simple like a pulse. It is not a pulse in the sense it is not a very short microsecond pulse, but rather it is a weak RF pulse applied continuously. So, it is not a pulse, but weak RF irradiation applied continuously for a duration of 60 to 80 milliseconds. Now, during this period what happens is the hydrogen atoms in one molecule starts getting coupled to hydrogen atoms of the other in the same molecule. But remember, in a case of a standard COSY, the coupling takes place only because it goes from one hydrogen to the directly coupled hydrogen. But in case of an isotropic mixing, it gets coupled not only to the next neighboring hydrogen, it will also be coupled to little bit far away hydrogen, not directly because of J coupling, but indirectly because it is coupled to a intermediate hydrogen. So, let us see more in a pictorial manner how we can understand this. So, let us say we have a molecule, again take the case of propanol. Here let us label this as 1, 2 and 3, these are 3 hydrogens. So, we saw that in case of COSY this is what we will get, this is in case of COSY, but in case of TOCSY you will get from here to here and then again from here to here. So, this is in case of TOCSY. So, in a TOCSY experiment you actually go from one hydrogen to a far away hydrogen, that is from 1 to 3 because of the intermediate coupling to 2, because 1 is coupled to 2 and 2 is coupled to 3, the 1 gets coupled to 3 in case of a TOCSY, but not in the case of a COSY. So, in the case of a COSY this is not possible. In the case of a COSY, the transfer takes place only from the nearest neighbor hydrogen atoms. So, there is no transfer from this hydrogen to this side to all the way up to 3 in a COSY, but in a TOCSY experiment, because we apply what is known as isotropic mixing, what happens is that because of the intermediate, the magnetization first flows from here to here, then it gets transformed from here to here. So, this is why now we can say that the information of 1, the chemical shift of 1 starts getting correlated with the chemical shift of 3. So, we will see that as we go on, but this is a special feature of TOCSY that it couples two hydrogen atoms which are not directly coupled to each other, but still they are actually coupled through intermediate coupling. So, suppose that these two did not exist. Okay. So, let us assume that, for example, let us say this was something like a ketone group here and there was no hydrogen here, then this to this coupling would not be possible also in a TOCSY, because there is a break in between. If there was suppose a break here, that means suppose there was no hydrogens here, then there would be no mechanism, no way for this hydrogen to couple to this even in a TOCSY, because it needs this intermediate coupling. Okay. So, this kind of a break is possible in some molecules, and that will separate this side of the molecule from the other side. We will see some examples of this as we go along. So, now the two things is, one is what is this isotropic mixing actually. So, isotropic mixing is doing what is called as, it makes the spins go into something like strong coupling scenario. So, because of the time restrictions and because this is a basic course, we are not going to go into the details of how exactly the strong coupling happens, but we have to just keep in mind that in general COSY, a normal COSY, we are in what is known as a weak coupling situation, and when it comes to TOCSY, we make the spins go into a strong coupling situation. So, let me briefly tell you what is this weak coupling and strong coupling. So, weak coupling we define as the chemical shift of two hydrogens, let us call it omega I minus omega S. So, let us say these are the chemical shifts of two hydrogen. The difference in the chemical shift is much greater than the J value, J coupling. If this happens, we say that the two spins are weakly coupled, but if the reverse happens, if omega minus omega S is, let us say, almost similar or less than the J coupling, that means the two spins are so close by that their interaction or their the difference in the chemical shift is smaller than the J coupling. When can this happen? For example, let us say it happens when the chemical shift is almost 0. Suppose these two spins I and S, suppose let us say that their difference in the chemical shift is, let us say, almost 0. For example, let us take it is at 7, one is at 7 ppm, other is at 7.001 ppm. So, on a 500 megahertz, if you calculate 001 ppm corresponds to 0.5 hertz. Now, 0.5 hertz is very small. The J coupling typically of the range of, we saw that 5 to 10 hertz in general between two protons. So, you see we are now, if the protons are very close chemical shift values and their difference is smaller than J coupling, then we say that these two are strongly coupled, these two spins. And in a strongly coupled scenario, things happen in a different manner compared to what happens in a weak coupling. In the case of weak coupling, the chemical shift difference is much greater than the J value. For example, let us say that you have a peak at 7 ppm and there is another peak which is 7.1 ppm. So, difference is 0.1 ppm, and you can consider, let us say, 500 megahertz spectrometer. So, the chemical shift difference of 0.1 corresponds to 50 hertz. Now, 50 hertz is much greater than 5 or 10 hertz, which is the typical J value between two hydrogens in general. So, therefore, those two spins, that is 7 and 7.1, now we will call it as weakly coupled. In this case, in TOCSY, what we do is, normally the spins are always weakly coupled, but by doing some technical thing like applying weak RF radiation, we create a situation where the chemical shift difference between the spins are lost, and because of that they enter into the strong coupling scenario. So, how does happen? As I said, that we will not be able to go in detail. For the more details about this, there are excellent books, that is the standard textbooks which we have recommended. You can look at that. So, the idea is that you apply an RF radiation, such we use the word spin lock. So, you will come across this word spin lock in the textbooks. The spin this application of a weak RF is, we also say that we apply a spin lock. So, when we apply a spin lock, we essentially create a situation in which the chemical shift difference between the two peaks or two atoms goes almost close to 0, and therefore, the J coupling does not go to 0, and therefore, if the chemical shift difference becomes very less compared to J value, it becomes strongly coupled. So, by when the strongly coupling when strong coupling happens, this thing starts happening, that the spins start interacting with remotely coupled spins even though they are not directly coupled, but because of the intermediate hydrogens. So, this for example, in this case the hydrogen 1 shows interaction with 3 not directly, but through the intermediate hydrogen atom 2. So, this is the basic idea on a TOCSY, and the advantage here is that you get interaction between all the hydrogens which are coupled to each other. Okay. So, we will look at that now. So, let us say mathematically, let us see what happens. So, we have applied a pulse, a 90-degree pulse to one spin A. Now, that spin A starts evolving because of chemical shift here. So, that is what is represented mathematically by cos omega t. So, in this case it is spin A. So, we say omega A, and this time period here is denoted as T1. Okay. So, now during this isotropic mixing, as I mentioned, you basically see that the interaction of A not only happens with B, but it also happens, let us say, with another spin which is remotely coupled through B. It is coupled not directly to A, it is coupled to B, B is coupled to A. So, A gets coupled to C in a case. So, you see we can call this type of a scheme as a relayed COSY. So, if you know, in a relay race, typically what happens is there is a first runner, he carries the baton with him, he runs for some time, transfers the baton to the next person, and the next person then runs for some more distance, he gives it to the next third person, and so on. So, this is called a relay race. So, similarly we are having a relay magnetization transfer here. We first evolve A, then transfer the magnetization to B, and then B does not evolve, but B because of J coupling to C gets transferred to C, and so on. And finally, after all the transfer has taken place, we then evolve the chemical shifts of those B and C. So, which is shown here by two chemical shifts here. So, cosine omega B T2 and cosine omega C T2. So, you see that what happens is that because of this coupling, because of the spin A to B, there is a transfer of magnetization from A to B, and during this period B to C also transfers takes place, and that is therefore you get the chemical shift of C as well in the FID. So, the final FID now contains not only the chemical shift of B, but also it contains the chemical shift of C. But where is the chemical shift of C coming from? Because from transfer from A to B to C. So, this is what happens in a TOCSY, it correlates. So, it correlates all homonuclear chemical shifts that are coupled together through J coupling, but remember they may not be directly coupled to each other, but in a group, they are coupled in a group. So, we can say this belongs to one group. Okay. So, they belong to one group in which one is coupled to 2, 2 coupled to 3, and vice versa. Okay. So, this is how this is the information which you get in a TOCSY spectrum. We will see more schematic and real spectrum down the line. And then what is the spectrum look like? As we saw in the case of COSY, you expect a diagonal peak. So, remember here, if you look back in this picture here, the spin A does not transfer all its magnetization to B and C and so on, it only transfers part of it. That is what we mentioned in the last class as transfer efficiency. So, the transfer efficiency of magnetization is never 100% in case of homonuclear. In heteronuclear, yes, you can achieve 100%, we will see that later, but in homonuclear we will not get 100%. So, whatever does not get transferred and remains on this spin will evolve again with spin A here during T2, right. So, what you have shown here is only the transferred part, but the non-transferred part, if you recollect in the last class we saw that like in the COSY, the non-transferred part also remains, and that will evolve first here during T1 with omega A T1 cosine omega A, and then it gets transferred, it does not get transferred, it remains on A, it will again evolve with the chemical shift of A. So, that is called as a diagonal peak, and that one which gets transferred, we use the word cross peaks. Okay. So, let us see the spectrum, how we expect for this particular molecule, again the same system which we saw in the last lecture. So, this is propyl chloride. So, the hydrogen atom 1 is here, 2 is here, and 3 is here. So, if you record a standard 1D spectrum, Again, for the sake of simplicity, we are ignoring the J multiplet pattern. So, if you record a standard simple 1D proton spectrum, you expect this kind of spectrum peak pattern. Now, if you go to TOCSY, where you see in the horizontal axis is hydrogen and the vertical axis is also hydrogen. So, both these axes are hydrogen. So, now let us draw what we expect for this particular molecule. So, like in the COSY, we first get the diagonal peak, which are nothing but the peaks coming at the same position. So, for example, 1 ppm, 2 and 2 ppm, 3 and 3 ppm for this. So, you see this is diagonal peak is nothing but a simple 1D itself on from the both axes. So, this has no value for us, but it is always present, we cannot avoid this type of peaks. Then let us see cross peak. So, like in a COSY, you expect direct cross peaks because the direct coupling is there between 1 and 2. So, even though you do not need TOCSY for this, COSY also gives the same information, but TOCSY also contains COSY inside it. So, that means TOCSY is similar to COSY in that respect, because it also has the same peak pattern between the neighboring hydrogens like we have it in a COSY. But what is more important in TOCSY is the further interesting information between 1 and 3, which I will show you now. So, this is again between 2 and 3, which is not very surprising. This is similar to what you get in COSY, in a COSY spectrum, because this is the direct coupling between 2 and 3. But in a TOCSY, what will happen is you will get an additional peak shown here, orange color peak. And where is that coming from? That is coming because of this here 1 to 3 coupling through 2. Okay. So, remember there is a through transfer. So, you cannot get this direct coupling straight away, you need an intermediate relay, you need somebody to relay the magnetization from this side to this side. So, if I remove these protons here, I would not have got these peaks. Okay. So, now we see all of these 3 hydrogens, 3 types of hydrogens are now showing all complete coupling to each other. So, if I have 3 hydrogens, I get 3 into 3 9 peaks. If I have 4 hydrogens like this, we will have 16 peaks. So, square of the number. A very simple idea, because it is just that all are coupled to each other. So, you will get a square number. Okay. So, this kind of a pattern, this kind of atoms in this molecule like this, which are coupled to each other, all of them, that is known as a spin system. So, this is a very important terminology in NMR spectroscopy, it very often used everywhere. So, in this case, how now we have come first time to this terminology. So, let us look at it more carefully. So, the idea of a spin system. So, what is a spin system? Spin system is basically a set of hydrogen atoms, protons, which are coupled to each other. There is no break in the coupling, and all the 3 together a set. It forms a set of 3 hydrogens, which within them they will be coupled to each other, not directly but indirectly in this case, for example, but they are A is coupled to B, B coupled to C, and within them they are all coupled to each other, and that set of atoms, spins, we call it as a spin system. So, if you if you record a TOCSY for a spin system, basically all the hydrogens in that spin system will show like this coupled. So, if there are n hydrogen atoms in a spin system, in a TOCSY you will get n square number of peaks for that system. Okay. So, this is the basic definition or the meaning of spin system. So, again we repeat, the spin system is a set of nuclei, that is it can be either protons or carbons. So, set of nuclei that are J coupled to each other within the set. Okay. So, this is a very important point in NMR in general. We will use this nomenclature as we go to more difficult or more advanced aspects. So, now let us see for an actual experimental spectrum. This is a spectrum taken from the book Neil Jacobson's Introduction to NMR. There we have shown for this heptanone. So, now we will look at this concept of spin system which comes out here. So, now if you see this structure of the molecule, what do you notice? You will notice that there is a break here. This carbonyl is kind of a break, because on this side these 4 hydrogens 4, 5, 6, 7, they are all coupled to each other, in the sense 4 is coupled to 5, 5 is coupled to 6, 6 is coupled to 7 and vice versa. So, in a TOCSY I would expect 4 to 7 interaction, not directly but through the intermediate, but this is not going to be the case for between 4 and 2, because remember, as we discussed in the last slide, there is an intermediate carbon, it does not have any hydrogens. So, there is a no direct coupling between 2 to 4, and therefore, indirect coupling is also not possible, because there is no hydrogen here which will carry the magnetization from 2 to 4. So, there is a break here. Similarly, but here is side 1 and 2 will be coupled to each other. So, you see this portion of the molecule, we will now call it as one spin system, and this portion of the molecule will be called as a second spin system. So, that is what is shown here. If you look at this spin system set of spins, then you see there is an interaction between them. So, you have H7 with H6 with H5 with H4, similarly H4 to H5 to H6 to H7. You see there are, if you count the number of pins, it is a square. So, 4 into 4, 16 peaks you will notice in this spin system. But if you look at 1 and 2, which is shown here with the red arrow, they are only coupled to each other. So, there is only 4 peaks, 1, 2, coming down 3 and 4. So, 2 into 2, 4. So, you see this spin system which has only 2 hydrogen atoms will be now only 4 peaks. So, this is how in NMR we can distinguish or differentiate spin systems, because within the spin system the TOCSY will have all the couplings, whereas between the spin system they will not have any couplings. So, NMR TOCSY experiment is therefore very useful, because now you can identify 2 spin systems here in this molecule, which you could not have identified from a COSY, because in a COSY you would have seen 2 to 4 all only one bond interaction. Of course, there in COSY you would not have seen this also 2 to 4, that would have probably helped us to also figure out the presence of 2 spin systems in this molecule. But TOCSY is a very clear cut way to find out, because all the spins which are coupled to each other will show a clean the 16 peaks, because there are 4 into 4, this side will show 2 into 2, and that will denote a difference. So, this is very important when it comes to amino acids in proteins and peptides. There each one amino acid we call it as a spin system. So, in amino acid you have alpha, beta, gamma, delta carbons. There within one amino acid there is coupling to each other, but there is no coupling between 2 amino acids in a peptide. So, in a TOCSY experiment, J coupling is not there between hydrogen of one amino acid to the hydrogen of a neighboring amino acid. So, what happens is that there is a break because of the peptide bond in case of peptides, and we say that the one amino acid is kind of separated or isolated as far as proton J couplings are concerned from the neighboring hydrogen, and we use the word spin-spin coupling. So, this is an example. Now, let us see how can we compare COSY and TOCSY. So, you see this is the same molecule here, heptanone, and you can see in a COSY we see only the direct coupling, which is what we saw, that it only gives you the direct 3 bond or J coupling peaks pattern. Similarly, here to here it gives you only from 7 to 6, but in a TOCSY you see all the couplings everywhere, in the sense all the peaks are coupled to all other peaks because of this through bond, through transfer, through protons. But again, one spin system is separated from the neighboring. So, obviously, you do not get the between the 2 spin systems, but within one spin set of spins you get all the correlations. So, now you can, if you look at compare these 2 pictures, what is this telling us? It is telling us that the COSY concept, the COSY peaks are actually all present in TOCSY. So, which means COSY is a subset of TOCSY. Okay. So, TOCSY is much higher, more peaks available present than COSY. So, at in some applications COSY will be useful where you are not interested in looking at spin system. Suppose you are interested only in looking at what hydrogens are coupled to what hydrogens directly, then COSY is sufficient. But if you are interested in forming a spin system, then we use the experiment TOCSY. So, it depends on the type of application which you are interested. So, typically when we go to small organic molecules compounds, we do not go for TOCSY, we usually are satisfied or sufficient to have a COSY for structure analysis. But if you are looking at peptides and proteins, there you have to have a full fledged TOCSY spectrum, because there our job is not only to identify one amino acid, there will be several amino acids in the chain, in the peptide chain or a protein chain, Therefore, there it is much more difficult system to handle, and there we would need TOCSY. So, this brings us to the end of TOCSY experiment. So, we have seen now two experiments, one is the 2D COSY and 2D TOCSY. What we will do now in the next class, we will go to a new experiment known as 2D nuclear overhauser effect spectroscopy, that is 2D NOE-spectroscopy.